I'm delighted to introduce Professor Karan Jani, who's joining us from Vanderbilt University. So Professor Jani did his undergrad at Penn State and his PhD at Georgia Tech before taking postdocs at Georgia Tech and later Vanderbilt, where he is now an assistant professor of physics and astronomy and the Cornelius Vanderbilt Dean's Fellow, Faculty Fellow. A two-time honoree of the Forbes 30 Under 30 in science, Professor Jani is an expert in gravitational waves and the observatories that hunt for them, on the ground, in space, and on the moon, which we'll be hearing about today, along with some exciting new AI approaches to gravitational waveform analysis. There are still just a couple of meeting slots open, so after the talk, I encourage you to snatch those up while you can, and of course join us upstairs for lunch afterwards. And Professor Jani, it's a pleasure to have you, and as soon as I attach this mic to you somehow, the floor will be yours. Welcome. One online is going to hear some bluffing noises. That's good stuff. Just anywhere near the top.
It's
a pocket or a belt loop. Yeah, perfect.
Perfect. Right. Well, thank you. It's always a privilege to be here at Harvard. Thank you, Priya, for inviting, and thank you, Danielle, for being such a generous host. This is my first time speaking at the Black Hole Initiative, so I hope I'm able to sort of give a broad overview both from the astrophysics side of the things, but also particularly of interest to me and my group is black holes, but through gravitational wave. So, so I'm very glad to speak about it. It's an interesting time. We just celebrated our 10th anniversary of gravitational wave discovery from LIGO. So the first event was seen in September 14, 2015. And sort of that gives us a sort of time, both in the funding climate and otherwise that we are in, to think about what is the future of the field from this stage that we have seen, what we have seen about the universe in the last 10 years. Where do we go next? And the two frontiers that my group has been heavily involved now is not particularly because it's sort of the trend of the time, which is to think about using AI, but it's something very foundational to the way we do gravitational wave data analysis. And the second aspect that has surprisingly opened up, was not thought about for several years before, is what does gravitational wave astronomy look from the moon? So I would begin first by acknowledging that all the work that is being presented in the slides is done by my group, my PhD students and my postdocs. We are about, at any given time, 6 graduate students, 4 postdocs, and several enthusiastic undergraduates who are working on these things. I am a senior member of the LIGO-Virgo-Kagra collaboration, which is the sort of gravitational wave collaboration that we have for Earth-based detectors. My group and myself, I'm the core member of also the International LISA consortium, which is the next flagship mission from European Space Agency going into space. And then we are building our own collaboration now, which is LILA, that I'll get to speak about. The nature of the work that we do is sort of reflected in my appointments. I hold secondary appointments in data science and electrical and computer engineering, and that has to primarily do with the 2 new frontiers that we have opened up. I serve as the founding director of Lunar Labs Initiative, which is the host of of LILA. And then we have an initiative for gravity waves and fluids, much inspired from the Black Hole Initiative. And I can see a few of you all from here have been part of and have visited us. I'm also a faculty mentor in the Fisk Vanderbilt Masters to Bridge program, which is one of the pioneering programs in the country that has brought in great astrophysics PhD students, including some of this in the audience. So proceeding, what we call the Earth-based gravitational wave network is broadly, and you'll see me refer it in the acronyms, the LVK, which is the LIGO-Virgo-Kagra collaboration. There are 2 LIGO detectors in the United States, one on the near East Coast, Louisiana, where I have spent time as a graduate student and where my graduate students mostly are stationed at when they are working on the detector, such as now when the observing run is going on. This is a full-time facility because gravitational wave is an all-sky search. We don't have to be at the telescope in night hours in winter, so it's rather pleasant to be in Louisiana in any given time of the year. And the other facility is the LIGO in Hanford. Hanford historically has been a nuclear testing site. Around that place is now the gravitational wave detector. There are two additional gravitational wave detectors, one in Italy, which is Virgo. I've been there a few times. In my view, it is one of the most prettiest looking places where a gravitational wave detector exists. There is one in Kagra in a mine in Japan. And then the final one, which would be built in 2030s, is the LIGO detector in India. Now, all these detectors have the same fundamental detection technique. That is, you have suspended test mass, which act as free fall mirrors or test objects, and you're trying to do Michelson interferometry and trying to look for change in path length. All of them have the same thing. However, based on the subtle changes, both environmentally, geographically, geologically, and from the people that are involved, each detector has a very unique sensitivity to gravitational waves. And currently, the LIGO Livingston detector is generally the most sensitive gravitational wave detector of all. That is where we are right now. In 2030s, the next frontier of gravitational wave astronomy will come in, which is the Laser Interferometer Space Antenna. Professor Natarajan was here, part of the inaugural study team of the NASA LISA. This is a sort of a very equivalent, I would say, to almost like what James Webb Space Telescope meant for the electromagnetic astronomy, is equivalent meaning for the gravitational wave community. It's a flagship project that is going to deliver incredible science that generations of PhD students and people can build around. This is an unusual space mission. The size of the interferometer is twice the diameter of the sun. It's a 2.5 million kilometer separation. For example, LIGO is 4 by 4 kilometer. Other Earth-based detectors like Kagra and Virgo are 3 kilometer by 3 kilometer. In that regard, this is 2.5 million kilometers. And it has to have that kind of a scale because you can almost think of the interferometry length is proportional to the wavelength of gravitational waves that you're trying to observe. So if you're trying to observe long wavelength, which means very small frequencies, you would end up needing very large bays. The entire mission is supposed to last around 4 years with an extension up to 10 years. But in that time frame, a lot of great science would be delivered. And we think about the spectrum of gravitational waves, the way we think about electromagnetic spectrum. The LIGO detectors are equivalent to what I would call an high-energy X-ray telescope. These are high-frequency transient burst events. So they are loud when two black holes collide, when two neutron stars collide. It's a quick transient event. They all happen at high frequencies. LISA is more equivalent to your infrared telescope. You have sort of a longer time you would see signals. Signals in LISA would generally last for years, months, or in that time scale. In most cases, essentially the mission lifetime itself. Versus all signals in LIGO are less than a second for at least black hole collisions. And then we have the another frontier. I haven't spoken about it much here in the earlier slides, but this is the pulsar timing, which had a breakthrough discovery of the stochastic gravitational wave background that can be summed up from all supermassive black holes that may be in spiraling, not merging. That happens at the nanohertz frequency, which is
not detection, evidence.
Evidence for the stochastic gravitational wave background, unlike LIGO, which all discoveries are quote unquote in particle physics language 5 sigma discoveries. Pulsar timing array is an evidence. That is, in analogy, same as your radio telescope on electromagnetism, right? It is a sort of a very low frequency. In between all this, is a sort of a nice gymnastic of all detectors we can have. There is a mid band which simply cannot be accessed by LIGO, nor can be accessed by LISA. And both have to do with technology and environmental challenges. I'll speak about it a bit later. And that LILA detector is what we would call essentially a visible light equivalent in gravitational wave spectrum. One can think about this spectrum itself as a direct direct reflection of the black holes that we would observe. So at the very lowest frequency, we see in spiral of black holes that are billions of solar mass. Then 3 orders of magnitude later, it's almost a 1-to-1 relation. At LISA, you see mergers of million solar mass black holes. LIGO sees mergers of tens of solar mass black holes. And that means naturally the mid-band lies where what we call the intermediate mass black hole range of about 100 to tens of thousands solar mass. Right? So there's a sort of a 1-to-1 map of the black holes and the astrophysics that we can do out of each individual detector. There is a huge science case for years that has been going on for the mid-band gravitational wave detector because there are sources that neither LIGO sees nor LISA sees. One such source is the progenitor channels of type 1a supernova. If they come from double white dwarf mergers, that would not be seen by LIGO, that still does not get seen by LISA. And then there are other evidence, like there could be complementary signals. For example, the binary neutron stars can still be seen by that. It's highly sensitive.
The mass black hole that you think LISA will be able to see?
The minimum mass of black hole it would see is all LIGO range because it will still capture the LIGO black hole up to tens of solar mass, but it will not go to. No, it would overlap. So the lines actually go much to the detector. Any detector we would build in mid-band would expand at least an order of magnitude in both direction.
I'm asking the other way around. Can LISA cover that region?
LISA can see those black holes, you're right, but they will not see them with the significant signal to noise ratio to be seen far enough.
Okay.
Far enough. Well, that's a fair point. It will see the in spiral of it.
So whenever we draw like sort of these constraint plots for, there's always these future experiments, which is like Einstein telescope or something like that. And those seem to cover this frequency range you're talking about pretty well because they go so deep.
Yeah.
They cover, so why, like?
They only go up to 5 hertz.
Okay.
The Einstein telescope. They don't go up to,
10?
this is 0.1 hertz.
Oh, I see.
The mid-band is roughly, I would define it as, 10 hertz to 0.1 hertz.
Okay.
Right? So there is this still new science that, the current detectors are not covering. That's why we want third generation detectors to come in. And that is where a lot of time is being thought about right now, that now that we have over 10 years, what are the next 10 years look like? One of them is the science case for mid-band. But just to come back of what we have learned in the 10 years of LIGO, this is every gravitational wave discovery that we have had. These are 218 unique gravitational waves we have seen. By unique, that means there is no repeating. I mean, there's one merger has happened, the source is done, and these are all sort of what we can call as a unique gravitational wave events. There are more than 218. These are the 218 that we have published to the world outside. The first detection is the famous GW 150914. We use the telephone number that starts with GW, and then it's the date of the day when we discover gravitational waves. But now we see multiple gravitational wave detections in a single day. So then you add even more complications of hour, minute, second. So they are very long names. I'm not going to call them by their individuals. And the observing run is still going on. We'll be continuing up to the end of this month, the fourth observing run. One thing here to quickly see is how rapidly the field is becoming data intensive. When I started my PhD, there was 0 gravitational wave events. And I was very happy that in my PhD, I could claim 3 gravitational waves in the abstract of the thesis. By the time I was doing my first postdoc, we added 9 more gravitational wave events that included the first multi-messenger discovery. Second postdoc years, then we had this catalog. We could not remember the names anymore of the gravitational waves we were seeing. And then this is everything that now my students and postdoc work on. So we have a catalog that we call the gravitational wave transient catalog that was published.
Are all those transients mergers? Or?
All yes, that's a good point. All gravitational wave events seen so far are coalescing compact binaries. I would not use the word merger unanimously here because that does reflect a binary black hole. When a black hole collision happens, LIGO does see the merger. But we have also seen binary neutron star where we don't see the collision, but we see the inspiral so late enough that it's inevitable that the two are going to collide. The current count is that we have seen about 98% of all events are collision of 2 black holes. Now, the way we interpret here that what we are seeing is compact binary is essentially without any astrophysics. This is a purely a relativist regime where we have a data that is collected in LIGO. This is the 50914 signal. You can see the time frequency. This is the actual data in the LIGO detector without any assumptions of general relativity. We then take the wavelet time domain signal, match with the general relativity, which we do using numerical relativity simulations. That was much of my part of my PhD thesis at the time. We match the signals. We do that for a series of different ways. We come up with approximate solutions of general relativities for two-body problem. And from there, we get an estimate of the mass and the spins of the black hole. Right? This is for the first detection. This is a nice sort of infographics to show that if the two black holes were coalescing around India, it would have this sort of relative size. There's an actual size to the black holes I will see. And this is what we do for every single gravitational wave discovery. We go through the same pipeline to get an estimate of what the masses are. And then we get also some constraints on what spins are.
Sorry, I lost you. Size. What do you mean? That's not the actual size relative to the size of India, is it?
So, no. It is
What
not.
is the size? Yeah.
So this one is 60 solar mass. So that should be only 180 kilometer. But with the spins added, yeah, you are right. I have to double check the LIGO India webpage on that. But just for
Somebody's atlas.
yes. Yeah, there would be a little bigger black holes than the ones we have seen. Good catch there.
I would like those.
So not showing any relative. Not showing any relative length compared to any cities so that we don't claim a black hole is coming to us. This is a scale of every event that we have seen. The y-axis here is solar mass. The x-axis here is just in the rising mass range, what we have seen. Two very quick surprises that you can spot. And when I started my grad school, it was long assumed that binary black holes are about 20 solar mass in electromagnetic spectrum as accretion, so the smaller black holes, on the supermassive ones, as accreting binaries. So LIGO should not see more than 40 solar masses of merger, because generally it is 20 plus 20. And the very first detection itself shattered that foundation, that no, actually all the electromagnetic black holes that we have seen only go about 20. These are all the magenta electromagnetic, which are accreting binary. This is all the binaries of black holes that LIGO has seen. The way to interpret this plot is one circle merges with the other circle and creates your remnant black hole, which has lost some of the mass as gravitational waves increase its spins, but this is what you end up getting. There are not only we have started finding black holes that are bigger than what EM astronomy was predicting. We've also started getting objects which we are uncertain whether they are black hole or neutron star. For example, between 2 to 5 solar mass, we have started seeing now several of these candidates, and LIGO observations alone cannot confirm. It can only give you mass. It cannot tell you if it's a neutron star or a black hole, at least in its current capacity. And then we have started seeing black holes in the so-called mass gap, where a supernova should have left no remnant. And this is the famous pair instability process that disrupts the star. In that very gap, not only we see there is a population that would naturally happen because of mergers of two black holes, but additionally there are black holes in there that are merging, and even outside the gap that are merging, which has been seen by LIGO. And this was absolutely not predicted before LIGO observation. One can explain through some or the other exotic channels, but this is not a confirmed sort of a sort of prediction or estimates we had before LIGO started. So my group's focus is primarily on what is the LIGO population above 100 solar mass, which is, I'll come to it, which we call the light intermediate mass black hole. This is a sort of a word we use so that the electromagnetic friends of ours don't get upset that we are calling IMBHs what they are not calling IMBHs. This is one of the major search results that has came from from looking for intermediate mass black holes in LIGO. I started that first search in LIGO when I was a grad student back in 2013, when the observing runs of LIGO had started. And even then we very convinced looking at the data that LIGO can see intermediate mass black holes of this hundreds of solar mass much farther than it can see binary neutron star or neutron star black hole, just from how loud this event are. But we didn't have any estimate, unlike for binary neutron star where we had binary pulsars. Now we have found about 8 events where it's absolutely confirmed that the secondary black hole after the merger is about 100 solar masses. And 6 of those events were actually found by doing archival LIGO search. So now the LIGO data is published. It's public. You can go and access it. You can build your own tools to reanalyze the data. And that's what my group did. And then we found additional evidence of black holes of this mass. And the one way these estimates work is that every observing run, LIGO gets more and more sensitive. So the things that look sub-threshold earlier, they now start looking more and more convincing. And a very recent discovery announced by LIGO, which is 231123, which is from the year 2023, fourth observing run, confirms there is essentially a 5 sigma evidence of 250 solar mass black hole. Yes.
So these ones that you found in the archive afterward,
Yes.
are they in that stem?
No, that stem is exclusively reserved for LIGO Virgo Kagra black holes.
I meant the previous one, the one where you had all the figures.
No.
This one.
This is also just LIGO Virgo Kagra. And in fact, this picture is also a sort of, just for public. If you see this blob, there is a signature of black hole. And if you see sub-threshold, they even look even weaker and weaker, right? So the work was led by my PhD student, Crystal, and postdoc, Anjali. We had also done the same exercise earlier with my student who's now at PhD student at Caltech, Rianian. And the LIGO Virgo Kagra collaboration has confirmed this event. So it's very interesting. Now, not only you have this population of 2 pre-merger black holes, so the black, by the way, I should say, it's the pre-merger black holes, and the red are the merging black holes. Yes, Lisa.
I'm surprised you can get a 5 sigma at that high mass. So how is that possible?
The way we compute it is to do, we have only for this particular one, the 231123, we look for the false alarm rate, and if the false alarm rate threshold goes beyond a certain threshold that we have said, it's like 1 per 10,000 or 1 per million years for different pipelines, we claim it's a discovery. The word 5 sigma can be not, please interpret them a bit loose, but they are confirmed gravitational waves in the same way as others are.
And how big, how long a time signal?
Oh, the time signal would be like 0.1 second or less. So you're only seeing an orbit before merger.
And you say you can get that, that's amazing.
Which is, I think, from how the tools have been trained now, that level of statistical significance, we are able to get if the event is loud enough in signal to noise. So this one was a loud event.
So it's pretty close.
It was closer than the earlier ones, yes.
Oh.
Right. And one point now that was a good point mentioned, we measure black hole masses in the source detector frame. So when LIGO sees a signal, it is already redshifted the way electromagnetic signals are redshifted. That is why what we estimate the mass is the detector frame mass. But then the source mass of the black hole has to be accounted for the cosmology. So if something is at 100 solar mass coming from redshift 1, LIGO would see this is a 200 solar mass black holes. And then because we have a constraint on luminosity distance, we then use Planck cosmology to find the corresponding redshift and then get the redshift source frame mass. So every time we report masses, it is the source frame mass, to not confuse the community. So this is the true mass of the black hole at the time of the merger, not the one that is redshifted. Yes.
Can you give a distribution of what the C's are for these, what redshift you're finding? The big ones then?
Oh, that would be, so I can give you the one famous one, the 1905-21 is roughly at around 4 to 5 gigaparsec. So that was about redshift 0.8, and we did have to correct for that. All right. Okay. Moving on. So how does this new cousins of IMBHs compare with the rest of the IMBHs? So this is an observational landscape of all intermediate mass black holes so far found in electromagnetic astronomy, and when you compare with the LIGO, Virgo, Kagra observations. And of course, they are very, very light, and that has to do with our own selection effect. LIGO is not sensitive to 10,000 solar mass mergers, which is what you would see the heavy IMBHs. And we have now internally started calling it, please don't get upset, the IMBH community, but we just call them heavy IMBHs is anything about 10,000 solar mass. Light IMBHs is anything less than 10,000 solar mass. Please stick with these words because there is an arbitrary line after for the supermassive black hole that is also confusing in the literature. Is it a million? Is it above? So the effect is really opposite. Like in stellar black holes, we found black holes that are way more massive than what electromagnetic astronomy found. And in IMBH space, we have started finding black holes that are much lighter than what electromagnetic astronomy would have found. And the astrophysical origin of this black hole is completely unclear. There is a lot of debate. How would you create black holes in a pair instability mass gap, and even above, how likely such a process can happen? It's uncertain. We have some number density rates, but all channels are likely possible. There was a channel that Priya, by the way, proposed that actually can explain all these black holes in this mass spectrum, could be coming from a fundamental process. Could be. We would be able to test this. I have to give a shout out to my grad students who wrote this nice conversation piece on much more mysterious cousins of the supermassive black hole. All right. Light IMBHs are also unique because they are really across the gravitational wave spectrum. You can start the intermediate mass black hole. You see the mergers in LIGO right now, but you can track back the inspiral several years, thousands of years, hundreds of years away before merger, and can track the environment around the binary. There's a very nice study from LISA on checking the environment, the eccentricity impact, which LIGO would definitely not see, because by that time, a lot of the binary is too close and we only see the signal for 0.1 second. It's very hard to make estimates. But LISA observations would see the orbital eccentricity. LISA observations could also find things like the kick of the black hole after the merger. So once the black hole 2 merges, the center of mass is not where the black hole relies, because there was a linear momentum being transferred along with the energy and angular momentum. So 100,000 years before merger, in fact, millions of years before merger, the black hole already knows in the direction it is going to be kicked at. It can kick at thousands of kilometers per second. It can kick at 90 kilometers per second. And that changes whether it will find another partner to pair again for a hierarchical merger. It's very hard to constrain kick from individual gravitational wave detectors because it's very sensitive to spin orientations. And then we have shown in a recent study that, in fact, when LISA observes it, and then after LIGO observes it, if you join the two things together, you can get an extremely precise constraint on what is the kick of the black hole. If this kind of heavy black holes happens in the disk of AGN, as it is predicted by several prominent groups now, then what happens is after merger, this black hole is just traveling in the AGN disk, and then weeks later or days later, it has a UV flare because of accretion, and it's traveling at a very high speed. And then what we have found is, multi-band observation is like very perfect to pinpoint on the flare and accuracy of time. But this is something that I'm particularly excited about the mission like LISA, because it opens this domain of multi-wavelength gravitational wave astronomy. The same way you do multi-wavelength electromagnetic astronomy all the time. In gravitational wave, of course, we have not happened because we've only opened one band, and we need multiple bands to open up. Yes, Ramesh.
That red event,
Yes.
why is its signal going up and down?
It's an intermediate mass.
Very simple monotone.
That's a very good question. It's an intermediate mass ratio kind of system. So it's 1,000 solar mass plus 100 solar mass. And because of the inclination angle or the viewing angle, you would see these higher tones that are being radiated. So it's not just the dominant mode, but the additional tones too. And they have this effect of, sort of increasing or suppressing the mode contribution. So instead of a simple line, you would see a more sort of a spectroscopic gravitational wave image from it. Yes.
Can I just follow up? So there's nothing to do with eccentricity?
No, this one is actually quasi-circular orbit. It's just from the mass ratio that this effect is. But it would also rightly happen with eccentricity or precession spin. Any asymmetry in the black hole would result in higher harmonics.
So is there a degeneracy there?
There is really, let me think about the degeneracy question. There is no degeneracy per se between how each mode is interacting in combination with the other modes, right? But each mode has a reflection of something which is intrinsic to the black hole. In some cases it's spin, in some cases it's the mass ratio, in some cases it is eccentricity.
It's optimistic, but I think in principle, you break the degeneracy by looking at the time dependence of the signal. Because you care about whether the precession is more like eccentricity is more whatever, right? I guess the other modes are just somewhere. So
Yes.
if you really do a detailed measurement.
Yes.
But yes, the data so far is determined.
Yeah, and also the primary reason being the data is so short right now. We are only looking at 0.1 second, 0.2 seconds, where the higher harmonics, in principle, the higher harmonics are strongest at the time of the merger. So the merger gives you the best sort of laboratory to test these nonlinear aspects of GR. And the X, yes. All right. Moving on, so this is where LIGO is right now. By end of next year, I think whenever we do the next public release, which will be a year after we end our observing run, the catalog would have at least somewhere around 500 to 800 gravitational waves. That's a lot of gravitational waves for doing amazing science with. But if we keep continuing LIGO into the next avatar, which is LIGO A+, and then there are plans for even further than that, and these are actual improvements to the detector. So you can think about changing the suspension system, how initial LIGO went to advanced LIGO, and then from advanced LIGO, the next stages could have cryogenic system. There are several planned upgrades. And then there are future detectors like Einstein telescope was mentioned. You would then start seeing the collision of binary black holes essentially across the cosmic horizon. This is a plot where each circle is logarithmic in redshift. So this is 0.1, 1, and then all the way far is, you can assume where the cosmic microwave background comes. And you see the density peaks because we are assuming here that the merger rate corresponds to the star formation rate. And that's why somewhere around 3-ish, we should see the most amount of binary black hole mergers to take place. In a data-rich time as this, like LIGO A+ horizon is this dotted line, what we can do to test the formation channels is not only the intrinsic properties of the binary, but you can in fact look at the global distribution of the binary with respect to other known things. For example, if we have, and this is from the illustrious simulation where we've done this, we had a recent paper out by my grad student Bill, and this plot is by our RU student Matthew. But if you look at the supermassive black holes, you look at the stellar mass, the stellar particles in illustrious, and you look at the dark matter halos. And then if you track where the binary black hole mergers of LIGO, of the stellar sizes, are happening, you can find some pockets where they should dominate if they all come from stars. But if they don't come from stars, for example, if they come from the disk of AGN, then the association is more closer to where the supermassive black hole of certain size would be. And then you can use the very large-scale structure as the probe for what the LIGO black hole origins are.
Can you actually distinguish whether, like, is the pointing that good that you can
That's a
say
good
whether
point.
it's coming from the AGN disk or the galactic disk?
The error bars would be sensitive to, I mean, theoretically, we're never going to reach a good enough scale where we can reach the angular size of galaxy, at least not with LIGO or not with Earth-based telescope. In principle, though, you can look at a statistical distribution and then try to find where more likely the correlation happens. Just how we do with PTA, for example, with the AGMs, right? All right.
Are you assuming no E&M counterparts?
We are absolutely assuming no EM counterparts here because so far in 10 years, we have only seen one. And even in the archival LIGO searches, when we go and compare with the Galaxy catalogs, or we compare with the ZTH catalogs, we still don't see any correlation of any spatial temporal correlation of gravitational waves with electromagnetic. And it does seem that the promise of multi-messenger is a bit fading. Yes, we don't see it. And it's unlikely we are going to see even with any ground-based detectors going forward.
Then how do you go about locating where the gravitational wave comes from?
The gravitational wave localization can still be robust, independent of having an electromagnetic counterpart attached to it. In fact, for binary black hole mergers, we don't really expect, unless and until they are surrounded in some sort of a gaseous environment, that where a peak, some sort of electromagnetic signature would happen so close to merger. For this masses, these are 10s to 50 solar masses. These are not the supermassive black hole mergers, right? Yes, Priya.
Think this is a little sketchy, right? Because if nuclear star clusters are the sites where these are forming, or they are forming in AGN disks, which are really proximate, I don't think illustrious can actually tell you that, or that even the observations can tell you that.
This is very preliminary step one that can large scale system be, but you are right. This is not involving any channels beyond assuming that the stellar particle cluster is where the LIGO merger rate happens. So this is really fine-tuned to make illustrious replicate LIGO mergers by semi-analytical models, and then trying to estimate. But yeah, there's a whole industry. I agree. There's a lots of caveat here. All right, moving to the two parts that I promised in the title, AI and the moon. So this one is something that we've been thinking around, because if you look at the amount of gravitational wave events we see even now, the gravitational wave data analysis is extremely computationally intensive. We are surrounded by a detector that is not your perfect data set. We are surrounded by non-Gaussian noise that are impacting major discoveries of LIGO. For example, I've just put as a comparison here. On the left, on the right here, you see all the things what we have identified as known form of glitches that is non-Gaussian noise from environmental and instrumental coupling with the detector. And you can think of this being earthquake. You can think of this being the scattering of light from the mirror. You can think of this being power lines. Several of this impact LIGO detector. And these are the identified ones that we know. We don't know where they are coming from in most cases, but we at least know they are repeating again and again. And in right, you have actual gravitational waves that are confirmed with the statistical confidence that you need to declare a gravitational wave event. And you can already see, this is not the same apples to apples with the z-axis here, but you can see it's very difficult to distinguish noise from gravitational waves, especially when the events are not very long lasting, like the one that Lisa mentioned. If the signal is so high mass, how can you be sure it does not look like what we call a blip glitch? And there is a lot of cleaning of data before even it reaches the public eye. We do a lot of data processing. The public data does not sort of give you, thankfully, it does not give you access to this. But what could happen is a glitch can sometimes overlap with a gravitational wave and can tell you things which are not astrophysical. For example, in one case, we found that the spins were extremely negative, like as if both black holes are spinning in the opposite direction of the angular momentum. Could happen, dynamical capture. But what we also found that there is a glitch happening only 1 second before it. And if you try to remove the glitch, then that inference changes. So there is some sort of a corruption in the signal that is happening because of instrumental glitch. So we had this broad idea, can AI learn the grammar of gravitational waves? And in that process, can it make sort of informed decisions of what is a signal, what is a gravitational wave, what is a glitch otherwise? And then can we go from there to build a foundational AI model that would do end-to-end gravitational wave data analysis for you, which is, by the way, when we have, I think the estimate is we are going to see about 50,000 events every year in the future detectors. And if you are seeing 50,000 detections every year, it's absolutely not possible to do it the way we currently understand gravitational wave data analysis. So we built this program with my group and the Data Science Institute. It's called the AI for New Messengers program. These are the postdocs, these are all our grad students, and there are dozens of computer science undergrads who do this as their capstone project. And what we have essentially given is take public LIGO data and use the tools that are the new tools of AI, and see if there are some sort of an interesting results that come up from that kind of work. And one of the work that has, I mean, we have published like series of work in the last 1.5 years. One major application was the OpenAI has this model called Whisper, which is trained on, I believe around 700,000 hours of human speech. So it's already a fully trained model with this like a million dimensional parameter space. And we lightly trained it on LIGO. So we took a sample of LIGO data. We trained it where we have identified what is gravitational waves and what is a glitch. And then for rest of the new observing runs, we just let it work and see if it can fundamentally tell what is a glitch versus what is a gravitational wave. And the results are, at least for now, promising. It actually finds most gravitational waves LIGO has discovered without knowing fundamentally what a gravitational wave signal is. It's not even trained on gravitational waves, it's trained on human speech. But there is somewhere the algorithm gets really good at understanding what noise are. Because the noise have a more repetitive fashion of being in the data compared to gravitational wave signals are. And we have about 90%, I would say, efficacy. This is the matrix shows the confusion matrix is glitch versus a true gravitational waves. And not only then, after it has found a signal, can it reconstruct the time domain wavelet feature without inherently knowing general theory of relativity? Can it know this is an inspiral of two black holes? This is a merger of two black holes, a ring down of two black holes. And not only it can do that, it can do it in situations, which is where you know it is effective, is suppose if you had a noise at the same time as gravitational waves. And so in this case, your injection would have, this, what we call this whistle noise. That is a repetitive whistling feature that happens. And there is a true gravitational wave signal right here, or the synthetic gravitational wave signal. And then it removes it and then finds the true gravitational wave signal and confirms it with at least to the level that we can do gravitational wave data analysis with.
The glitch is present in only one detector, right? That's
No,
why you call it a glitch.
That's true, but you could still have different glitches being present at the same time in the combination of detectors. So it is very unlikely, in fact, if you take 1 second of data across 5 detectors, all 1 second of data would have a glitch. Just a variety of glitches could be different. This is more sort of pressing because we are coming to places where our parameter space does not have a natural way to solve Einstein's equations. We can right now solve numerical relativity equations only up to mass ratio 4 with spins. So if nature produces mass ratio 10, which is spinning, we are relying on highly approximate solutions here. And that's why we need to find a way to denoise the signal and extract the signal with being essentially agnostic to the modeling that would be part of it. So this is a few results that have came out. A new result that we actually applied it on, so LIGO, we just announced a discovery of a 250 solar mass black hole, which is the most confirmed discovery of the light IMBH. We put our entire end-to-end pipeline, like search the entire LIGO data, find the glitches around. We actually had known glitches around the signal, and this was one of the hardest events for us to do the data analysis from, because different solutions of general relativity, which are approximate solutions, did not agree what the signal would be. That has never happened before. And in fact, we saw like individual detectors had different inferences. In this case, then we allowed the pipeline to confirm, like, it found in the chunk that was publicly released, not all of this chunk is publicly released LIGO data, in that very part where the true signal exists, it found it with a certain 90% or 80% confidence in 2 detectors. Then it reconstructed the signal. The machine learning reconstruction is, I think, this red curve here, and the other lines are what LIGO's reconstruction was. And LIGO already has a way to test model agnostic signals. And what we found, it's really more consistent with a model agnostic solution than it is with assuming general relativity for quasi-circular black hole mergers, which then means only one of the 2 things. Either there is a hint for new physics, which is not a statement that we would be able to make at any given years from now, or that there is possible new astrophysics, beyond quasi-circular orbit. It could be eccentricity, which would be very unlikely at this later stage in the merger. It could be gas effect that is still being perceived, but there is something in the signal that is beyond two black holes in vacuum spinning and colliding, right? And that is to some small degree of, we can see the residual, and within the residual study, we can find some spike to do this. And this has been confirmed otherwise too. This paper actually just got published, just got accepted in ABJ letters last week. So that's a result of where we want to move things forward. All right. I think I don't have much time to speak on it, but we are thinking more broadly. We just had a workshop on what is a foundational AI for multi-messenger astronomy. We are writing a Nature astronomy perspective from this, and it is really to do with a action plan, AI action plan that was released from the White House. It's a 30-page document where they talk about what is science-driven AI discoveries. Fun fact, it does not mention universities. I think there is just no known, conversation that is happening between the national leaders in AI and the kind of data and science and the problems that we are trying to solve with astronomy. And the pieces are going to be, the perspective is actually what are the strategic alignments in workforce development in AI that we find between multi-messenger. We have a variety of speakers from industry, so it was really great, and I'm happy to talk about it more later. Now to the final part, which is something that I have now, it's more sort of a focus of at least myself, and then my group is doing the LIGO and LISA and other amazing stuff with AI. There's a new era of lunar exploration that is happening. And this is much more mature than most in astronomy community, I think, sort of right now have an ability to know about what things are happening. Just to give a very basic primer. Since 2023, which is not too far ago, there has been 3 soft landings on the moon. Soft landings are hard because moon doesn't have an atmosphere, so you don't have to, if you go there, you can't just likely just crash. This is the Chinese Chang'e lander, which is on the far side, the first lander to reach on the far side. This is the Indian Chandrayaan lander. This is the Japanese lander, which had a soft landing, but it got tilted. So you can see it tilt, but it had the best camera on board because it got a really nice 4K picture of it. And then from the United States, there have been 3 landings, all by private companies. This one is by the Intuitive Machines, which landed and then also toppled. This one is from, I believe, from Firefly, where it didn't have a camera, but you can see a very nice shadow on the lunar surface of the lander, which is amazing. They actually have a video. And then this one is also Intuitive Machine, also tripped. But you can see the landers are sort of, so the legs of the lander are looking at Earth. Now, this is all part of a larger program that NASA has, which is the Commercial Lunar Payload Services Program. It's CLPS. And these are all the deliveries, the 10 deliveries to CLPS that are happening within this decade, each to different locations, each has a very distinct science payloads. So the way this works is NASA has a call right now for this, which is the payload research on the surface of the moon. They give you as PI one-time funds to make a payload. That is how all the 10 have been selected so far. That payload, then you deliver very aggressively timescale in 3 years or something. And the budget already includes your landing and launching costs to the moon. So the lander company is paid separately. The launcher, which is in most cases SpaceX, is paid separately. As a scientist, we are only sort of responsible for the payload. To get an estimate, it's about $500,000 per kilogram if you directly ask the private company to take it to the moon. It's not bad if one thinks about it right now. And that is what it is. So what a NASA administrator told us, think of this as your Amazon delivery to the moon. If you pay for it, they will take you. And it's not just they are taking science. They took the first landing, actually had, unfortunately, they couldn't get the nice ad, but it had a Columbia jacket sponsor advertisement because Columbia wanted to show that on the moon their jackets work amazing. But you get the point, right? This is happening. And the CLPS program is building up to be what would be the next big frontier for NASA. I hope everyone's reading the news lately, which is the Artemis project. The Artemis 2 would be the fly around to the moon, and then the Artemis 3 would be the first human landing. There are two companies that have been tasked to make the human landing system. One is SpaceX, the other is Blue Origin, and this would be a part of the first time NASA is returning back since the Apollo era. So this is a very heavy investment in the current presidential budget request. This is the program that sits in. So the national academies took notice of this. And this has been around for a while because one of the mistakes that Astro 2020 Decadal did was not to say anything about what astronomy can be done on the moon. And that was other decadals had rectified. So the geoscience, planetary geoscience, the fundamental biological and physical sciences decadal, they all had sections on things that can be done on the moon, the heliophysics, etc. So as a new study that is appointed by the National Academies, it's a mouthful, and I'll explain a very quick why each word matters. Key non-polar destinations across the moon. Non-polar already means you're not going to South Pole. That is a mission after Artemis. To address decadal level science objectives, that means it has to be a science that the decadals have endorsed. For example, multi-messenger is that one science. With human explorers, this science cannot be done by robots. It needs a physical human presence to do. And we've been doing this for now, this committee. I'm a member of this committee, along with members from astronomy. Joe Silk, may someone know, we are part of this committee. And our task is to give a recommendation for the fundamental astronomy, fundamental physics. And it goes even actually beyond that. The scope includes heliophysics, space weather, geoscience, biological life, everything. And from astronomy, a very strong science case is radio, because if you had a radio telescope on the far side, it can see the 21 centimeter cosmology. So it's a case that has been around for a while. And gravitational waves is one of the new cases that I'll speak about. So this whole has then brought us as a community to think about what is multi-messenger astronomy on the moon. And after a series of papers, which one of the first ideas happened in 2021 when I was visiting Professor Lisa Randall. There was a discussion, I think at the time it happened with Avi, and we came up with a basic science case of what the detector on the moon would look like. And since then, several groups have independently come to the same conclusion. The moon is spectacularly quiet compared to where LIGO is right now. If one had to build LIGO on moon, it would have discovered gravitational waves at least a few years before we could have done on the Earth. And the simple reason is we are corrupted by the environment. The Earth is noisy seismically, human anthropic noises quite a bit. And the biggest challenge is that we have to build this very large and sustain them, this very large vacuum chambers. While the natural vacuum on the moon, 1 meter above height, is already 2 orders of magnitude better than LIGO's natural vacuum is. And by the way, when the LIGO vacuum was made in Livingston, the entire town lost, I think, electricity for a week or something. It's still the world's largest ultra-high vacuum ever made. So the community then, so this unique advantage of the moon opens the mid-band gravitational wave spectrum, from which this US community project is now called LILA, which is the Laser Interferometer Lunar Antenna. I serve as the principal investigator, but there are like dozens of other people working on it. It's a two-phase project. There's a long-term project and there's a near-term project. The long-term and near-term is set by who's making the landers. Starship may happen in the heavy boosters, the New Glenn. Starship can happen in like 10s or 15s of years. And that would allow us to make a dream observatory on the moon that can discover gravitational waves to cosmic horizon. I'll speak a bit about science case. Or you can start with the landers that we already know can take humans to the moon, like the Blue Moon is one, where you can have 2 astronauts who'll be there, and they'll be setting up what we'll call like a GRACE kind of a mission on the moon. So I'll speak a little more about LILA Pioneer, the first stage. So the primary payload is about 100 kilogram. The secondary payload is about 20 kilogram. The separation between payloads is 5 kilometers. This is, of course, not to scale here. But you can imagine an astronaut would drive a lunar terrain vehicle, go there, set it up, and then you have this interferometer placement. That is all actually LISA is. LISA is not an extremely complex project. Once you're able to set up in free space, you can discover gravitational waves. There are certain challenges of power and keeping this thing running overnight, which we are working on. And then LILA Horizon is more complex. It will clearly need a Starship-like detector because the weight cannot be taken on the moon with the current generation of landers that we have. If you're more interested, I'll speak about it later. But now, coming to the science case, why this is so interesting. The binary neutron star, we have only seen one binary neutron star multi-messenger event. In 10 years, of the hundreds of discoveries we have seen, we can only see one multi-messenger event. And that has to do with two problems. One is you don't know early enough where the signal is coming from. So you know essentially at the time of collision, oh, something has happened. And second, the error is still like squares of degree or tens of squares of degree. If you had a detector on the moon, like LILA, the effective baseline is now your Earth-Moon separation, but then you also gain from the Doppler modulation if the signal is lasting long enough. A binary neutron star at 0.1 Hertz is about 5 years from merger. So the signal is in band for a very long time. And even 1 month before merger, if you had started seeing and give the data, this is what the future Einstein telescope detector would do 6 hours before merger. This is green is what LIGO, Virgo, Kagra can do. Post-merger, a detector on the moon already is like orders of magnitude better. There is just no ballpark comparison of multi-messenger astronomy from there. We would, even 1 day before merger, under 1 square degree, we would give 20 gravitational wave binary neutron star events versus anything on Earth is essentially 0, even like 1 hour before merger, right? Now you have to pass a certain threshold before you send out an alert. So the case is absolutely for going to the moon is to revive the promise of multi-messenger astrophysics, which is critical for Hubble constant measurement because you need independent light and gravitational wave signatures together. But we go beyond just binary neutron star. We go with the binary white dwarf. If they are the progenitors to type 1a supernova, we have an estimate of how many type 1a supernova happens, how many mergers happen, the distance at which a detector on the moon can see them. This is the average distance. So they would roughly see them up to 100 megaparsec. Huge amount of white dwarf mergers we can capture from that. The interesting science case, I'm not the expert on, but I'm very excited about it, is that there is no foreground around 0.1 Hertz to 1 Hertz. What I mean is if LISA, even if it's so sensitive, it has this white dwarf background confusion noise. At LIGO, you have other infinite sources of noise that you get you cannot eliminate. But in LILA, where the range happens, there is no foreground, so the primordial gravitational wave background. If the detector has to be sensitive to that, this offers one of the first windows where we can measure that. Right? And finally, my favorite, the light intermediate mass black holes. This is again the plot where you have the cosmic horizon. So this the top is your CMB. The red circle is what LIGO is sensitive right now. This is concentric circle of observable volume. It has a sort of funny increase in redshift, but this is redshift 3, 10, 25, 80, 600. All of LIGO that we have seen right now is just this circle. What LISA would see for million solar mass black holes or tens of thousands of solar mass black hole is roughly up to the maximum observable cosmic horizon, this black hole mergers. What LILA would see is the smaller set of intermediate mass black holes, the 1,000, the 100. That is what we are trying to catch. All right. So as I said, this is a huge team of people working on it. This is all the universities in the scientific collaboration. We have NDAs now with Intuitive, which is one of the lander companies, with Johns Hopkins Applied Physics Lab, which is our aerospace partners, Southwest Research Institute. We have international MOUs now recently we have an agreement with ISRO to look for the next Chandrayaan program for taking one of the probes. And most importantly, of all this exercise that we've been doing for the last 3 years, this year the House and Senate Appropriations Committee had a line item sort of recommending NASA for a US-led lunar-based gravitational wave observatory to expand the spectrum of gravitational waves. Right? So this is gearing up to be one of the flagship missions for the field. We have an in-house Vanderbilt Lunar Labs funded now majorly by the Templeton Foundation and the RIM Foundation that sort of helps us with doing in-house activities. I'm going to skip interest of time. The timeline, which is the most critical thing here, is this is where we are. We're doing pre-phase formulation and tabletop studies. Artemis landing is happening soonish. We want LILA Pioneer to be on the moon by 2030s. And that is a very strict deadline that I have to myself, that we have to not propose something that cannot be taken to moon by 2030. The more complex LILA can happen 2035 in conjunction with LISA timeline. And that has to be LILA Pioneer is also some sort of a pioneer pathfinder mission. So it has to test a few of those technologies. CQG, the classical and quantum gravity, which is our main journal in gravitational wave, has a focus issue right now on LILA. If you are interested in submitting any science case on LILA, please tell me. I am happy to give you an invite, have an invited article. But this is a more comprehensive. It has experimental aspect, the technical aspect, the lunar challenges, site selection, all of that is sort of, we are gearing towards it. And next week, there is still time if you want to attend on Zoom or in person. John Hopkins Applied Physics Laboratory is hosting the International LILA meeting. We have all industries that are involved with lunar will be there. Even if you just want to hear what others are doing in space right now, this is a great place. So just look up in Google lunar gravitational wave. Sorry, I should have had a barcode here. But this is our 5th meeting in round. We've had 5 meetings before this, and APL is our fifth location. Lots of press. Everyone is excited. Gravitational waves can be done on the moon. Skipping that. International Astronomy Union is also excited because this is a policy protection for the moon problem. And coming to my conclusion, which I will just stop now. Thank you. Sorry.
Thank you, Professor John. I think we have time for maybe one question in the room and then maybe one on Zoom, and then we'll adjourn upstairs for more questions over lunch. Angela?
Hi, great talk. Why put LILA on the moon as opposed to leaving it in orbit the way we do with LISA?
Well, that's a very good question. Why can't LISA observe 0.1 hertz? And there are proposals. I'm part of at least one of that proposal. The challenge is that if you decrease the orbit size of LISA, you have to account for the residual acceleration in the satellite from the photon short noise. And to navigate that, the amount of complex, the displacement noise you have to reduce by such a huge order of magnitude, this is all post-LISA possibility. So if we wait till 2050, which is there is a European Space Agency's Voyage 2050 call, where we have proposed this, there is a possibility, but not from any current known technologies. There is no known technology that can allow free-floating satellites to discover mid-band gravitational waves.
Mr. You mentioned intermediate black holes is coming from mergers of lower mass black holes. I think it's an idea I got from you. So,
Yep.
So why are you not talking about that?
So it is, but there is no conclusive hint we are seeing from constraints that LIGO has on spins, because they are so broad that if it was a second generation merger, we would expect the peak to be around 0.7 in spins, but we still see broad. So in the 90% confidence interval, it's 0 to 1, essentially. Just missing.
Does that change anything if they're coming from such mergers?
It would change our understanding of escape velocities of that host, because all mergers would generally be about 30-40 kilometers per second. In most cases with spins beforehand, they would be hundreds of kilometers per second. And if they get to still stay in the environment and have another merger, that means they are in some sort of a dense place where they cannot leave after that.
But would that change your observational strategy?
Which I started at the starting, like we are absolutely astrophysically agnostic. There is no assumption that anything we need about where these black holes are forming. In fact, we infer it back through things like the merger rate as a function of redshift or as a function of mass.
Do you want to do one Zoom question? Okay. So Camille Carlisle asks, the event GW190521 was previously suggested to be tied to an AGN flare, I think using ZTF data.
Yes.
Has that not panned out?
No. It was promising. I announced the discovery of 190521 on behalf of LIGO. And the ZTF discovery actually came just like a week before that. And what the ZTF discovery was based on was the public sky map that we released, where it is not the most precise multi-dimensional Bayesian inference, but it's a quick thing that we release out to astronomers. That allowed it to go to a much smaller distance. So the ZTF flare is actually much closer. And now with our confirmed 90% credible interval of where the distance is, it's just missing the ZTF distance by quite a margin. Except in very particular case where the binary is eccentric. Because if it's eccentric, which LIGO doesn't take into account right now, that means it releases less power. And to match the amplitude, we had to bring closer. So for a quasi-circular orbit, the answer is no. For eccentric, we have not seen anything since, so I'm not sure.
I think we should stop there and do questions upstairs.
Great.